Hi everyone, I'm Khojasta Ahmadi, and today I will be talking about the insertion sort algorithm implemented in C++. So before we begin to talk about how this algorithm works, I would like to talk about what this algorithm does. So it is basically a way of sorting an array in an ascending order by taking each element and finding the place that it best fits, and it takes one element at a time, finds the place that it's best fit, and then swaps with that element in that position. And then when the prior element goes back to its both elements swap, the swap is considered complete. It's considered more efficient than other types of sorting such as bubble sort because it requires a minimum number of swaps to order the elements. So how it works is that we take one element and we start with the second element and we move it one by one while making a partially sorted array. Now, as we talk about algorithms, there's one other important thing that we should discuss, which is the time and space complexity, because to generally talk about how efficient an algorithm is, we must look at its space and time complexity. To begin with, space complexity is the total space that is needed by an algorithm dependable on the various input sizes. What we mean by this is that the complete space that the algorithm takes, taking into consideration the number of inputs that goes into that algorithm. So for insertion sort in particular, the space complexity would be big O of 1. Why? Because the algorithm does not need any external or extra helper data structures to order it. Rather, it takes the same variables and it orders the array it performs the sorting within the same array. We don't take elements from one array and order it in another array. So if we were to take the input size into consideration, its complexity would be O to the power of n, O big O of n, where n denotes the number of inputs, as I mentioned before. Time complexity is another part of deciding how good an algorithm is. It basically is the number of operations performed by an algorithm to complete its task. And the best or ideal algorithm would be the algorithm that takes the minimum or least amount of operations to complete the swap or to complete the sorting. So for insertion sort, we have to consider three cases, because one being average, second being best, and the third being worst case. So average case would be when the array inputs essentially require one sort to order them completely. For example, this example, which is 2, 1, 3, 4. If the array inputs are in this order, the notation of the algorithm is O big O of n square. This is because the array has to traverse the for loop, the nested loops, so thus the n is to the power of 2. Best case would be if the array inputs are already sorted, such as 1, 2, 3, 4, and the O notation would be big O of n, since each iteration in the first element remaining is compared with the rightmost element of the partially sorted array. So what we mean is that the array would not traverse the whole nested loop. It would just not need any swaps. And the worst case would be if an array that is input into by the user is in descending order. So we have to take each element and we have to take it to its rightful place, which requires a lot of swaps. So this is generally the same case as the average case, because the loop, inner loop, outer loop, is performed and n times, and thus the complexity is big O of n to the power of 2. So before we begin, I would like to give a general demonstration. So if we look at this simple graphical representation, which I would like to open now. So if we look at this is the unsorted array. So it would start with the secondmost element and move it towards the right, because when it compares it to the first element, the first element is generally greater. So the first element needs to move to the right and the second element to the left. And it would continue this with each element until we end up with a completely sorted array. And it requires is an amount of comparisons but a minimum amount of swaps, and that's why it's considered to be the most efficient one. Let's run this program and see. So as we can see, the algorithm is quite simple. We have a for loop, and within that for loop we have a nested while loop. So the for loop begins with I is equals to 1, which is the second index, and then it assigns that index to key, and j's value is given as I minus 1. So whatever I is, j is just one number less than I, and then it checks if j is more than 0, and array of j, which is array of 0, is more than key, which is the second element. So what we're saying that if the first element entered in the array of first index is more than the second index, then the second index should be swapped with the first element. There should be swapped and j should be decremented. And then, but the swap is not complete at this stage. It just moves the bigger element, which is in the first index, to the right, and then since j is decremented now, it would move the element that we saved in key earlier, which is the second index, and move it back to its position 0. And now this is the print method, which is a simple step of a for loop, and this is where the user inputs are taken, which is the main method. So if we run it here, so we'll consider the worst case first, which is for elements descending order, and we can see the total comparisons, the sorted array, and total swaps. The total swap is initially less because swaps are incremented at the time when the swap is completely done. So the first element is moved to its own place and the second element back to its own place. So to explain this example that I give in depth, which is the worst case of this algorithm, an array that's in descending order, we have this unsorted array with us. So what it does is it starts with 1, and then it assigns array of I, which is 3, to key, and it assigns I minus 1 to j, which is 0. So these are the variables which we will be working with throughout this entire algorithm. It enters the while loop because j is more than or equal to 0, and array of j, which is array of 0, is more than our key, which is 3. So it does not compare with the index, it compares with the value 3. And then array of j plus 1, which is array of 0 plus 1 is 1, array of 1 is equals to array of j, which is this. So 4 is moved to this side. As we can see, 4 is pushed here, and now the spot remains empty. And since j gets decremented at the end of the algorithm to minus 1, the algorithm will not enter the while loop again. While loop gets terminated, and now we get to this final stage of the swap, which puts the key element in its rightful place. So when we array of j plus 1, array of j is essentially minus 1, so minus 1 and plus 1 cut out each other, key is 3, so array of 0 will be 3, as we can see here. So the element that we saved here is useful now here, and the first iteration is complete. For loop now, I gets incremented, and we have the second iteration of the for loop. Again, I is equals to 2, key is equals to 2 because array of 2 is equals to 2 itself. And then j is 1 because I minus 1 is 2 minus 1, 1. And then we enter the while loop. Is j more than 0 or more than or equal to 0? Yes, because j is 1. And array of j is more than key. Array of j is more than key. So yes, both conditions meet. Now array of j plus 1, which is array of 2, is equals to array of j, which is array of 1. So 4 gets moved to this spot. As we can see, 4 gets pushed here, and the array of 1 is empty. Then j gets decremented to 0 right here. J is now 0, and the condition of the while loop meets again. J is more than or equal to 0, and array of j is more than array of j is more than key, which is 2. So 3 is more than 2, and now we can enter the swap. So array of j plus 1, which is array of j plus 1, which is 1, is more than key 2. So it enters, and then 3 gets pushed to this side, 3 gets pushed to this side. So as we can see, 3 has gotten pushed to this side, as happened with 4. And now to explain this, array of j plus 1 is equals to array of 1 is equals to 0. So array of 1 will contain the element which is 3. So to explain this, let's look at this. Array of j plus 1, which is array of 1, this position will contain the element array of 0, since right gets assigned to the left. So we will have 3 in the position of array of 1 now. And j is decremented again, which becomes minus 1. So the while loop gets terminated. Now the loop exits, and the final step of the swap happens, which is array of j plus 1. J is minus 1 plus 1 cancel each other out, key is 2, and then array of 0 will contain 2. So now as you can see, we have an almost sorted array. So to complete this, we will move on to this third iteration, the third and final iteration, because I will not iterate, will always remain less than size, which is 4. So we will only have 3 iterations for this particular example. It will begin by I is equals to 3, key is equals to 1, because array of I is equals to 3. As you can see, array of I, which is 1, is equals to array of array of I, which is array of 3, is equals to 1. So key is equals to 1. I got confused a little bit there. And j is equals to 2, because 3 minus 1 is equals to 2. 3 being the value of I, and 2 being the value 1, and 2 ending up with 2 being the value of j. We enter, and after this stage is done, we enter into the while loop. J is 2, so it's more than 0, and array of 2 is more than array of array of j. We have array of j here, 4, at the index of 2, array of the index 2, which is the value is 4, which is more than key, which is 1. So we will have a swap here. Now remember that j is 1, j is 2, so j plus 1 becomes 3, and array of j itself is 2. So the value at array of j gets assigned to the index of 3. So 4 is pushed to this side, and now 2 remains empty. Then j is decremented to 1, and array of j plus 1, which is array of 2, gets the value of array of 1, which is 3 here. So 3 gets pushed to this side, and 1 remains empty. And j gets decremented again, and now we will move to the final iteration of the while loop, because after this j is going to be minus 1, and the while loop gets terminated. So array of j plus 1, which is array of 1, will hold the value of array of 0, which is array of 0 is 2 in this case. So array of 1 will hold the value of array of 2, array of 0, which is 2. So 2 gets pushed from here to this side, and now 0 becomes empty. And you remember how we saved 1 to key? Now the while loop is terminated, and we enter the final stage of the swap. And the swap will be incremented here, because we will have a swap with all these 3 elements against 1, and the swap gets completed here. So we will have array of j plus 1, minus 1 and plus 1 cancel each other out, it will hold. Array of 0 will hold the value 1, which is the value of key. So 1 that we saved here will move on, come to its own rightful place. And now as we see we have a completely sorted array. So this is how insertion sort works. It takes the minimum amount of swaps, and it compares elements against each other, and it makes sure that an element comes to its rightful place and then completes the swap. So it's considered very efficient because of its time and space complexity, and that's about it. Thank you for watching.